Hey guys, all right, so third one here is our understanding the limit, but this time from an algebraic approach, okay? So first of all, we'll do our bell work, review a little bit of what we did last class. So if you haven't done them yet, go ahead and pause that video. And if you have, well, let's see if you did them right. So the limit as x approaches 2 of f of x. So here we've got 2, which would be right here. And as we approach that from both the left and right here, we're going to be getting 3. Then we've got the limit as x approaches 1. So 1 is our asymptote here. And we can see that as we approach it from the left, we're going to negative infinity. And from the right, we're going to positive. Therefore, it does not exist. And a good little thing for us to write is that the left side does not equal the right side. That's how we know that it doesn't exist. All right, so let's then get into our lesson proper here, understanding the limit and algebraic approach. So we're going to consider the function f of x, and it's this absolute value function. And the graph of f of x is pictured right over here, okay? Determine the following limits here from the graph, okay? So the limit as x approaches a, where a is going to be 0 and 2 from the right. So the limit as x approaches 0 of f of x, we're going to use it, finding the graph first, okay? So as we approach 0 here from both left and right, we're getting -2, okay? And then let's do this one as well. As we approach 2, that's right here, okay, from the right-hand side, we're going to approach -4. Well, now let's do it using the equation, okay? So what we're going to do is we're going to literally just plug that value in. This is the first thing we can always try with a limit. Doesn't always work, but it's what we should start with. And so what we're going to do here is we're going to get 1/2 times the absolute value of -2 times 0 plus 4, and the absolute value minus 4. So of course, anything times 0 is just 0. So that's going to go away there. And then we're going to get 1/2 times the absolute value of 4, which is just 4, and then subtract 4, which is really 2 minus 4, or -2. So we can see here that we got the exact same thing. And we should often, okay? Now, sometimes we won't, but it's what we're going to try at least first here. Sorry, we will always get the same thing here. No, we won't, because when we're looking at it on the graph, we could have a hole. But anyway, if the function is continuous, we are going to get the same thing. So here, we should get the same thing as well, but let's confirm that. So we got 1/2 times the absolute value of -2 times 2 plus 4, and the absolute value minus 4. Now here, we've got -4 plus 4. That's 0. 0 times 1/2 is 0. So the only thing that's still left is this -4 at the end, and we get that same thing again. So the important thing here to understand is that when a function is defined and continuous at a value x equals a, how can the limit as x approaches a of f of x be found analytically? All right, so the key thing here, which I just kind of mentioned, is that that function needs to be defined and continuous at that point, okay? If it is, well, then that means that, not a lot of room here, but we'll write it in, f of a is going to be equal to the limit as x approaches a of f of x if f of x is continuous. And obviously, if it's continuous, it's defined, right? So it can't be continuous and not defined. That doesn't make any sense. Okay. So let's try and actually apply this then to these things, these equations. So the limit as x approaches 3 of this. Now this is polynomial. There's no way it's not going to be continuous or not defined. So we can go ahead and try that. Let's just plug it in. This is what we should always try first. And so we're going to get 1/2 times 3 squared minus 2 times 3 plus 3. Working that out, this is going to be 9/2, right? 3 squared is 9. Minus 2 times 3 is 6 plus 3. And if we put all that together, you can use your calculator. You know, we'll do it the simple way. We'll break it down step by step for you. So 9/2, -6 plus 3 is going to be -3. Then we need a common denominator there. Common denominator is going to be 2, so that becomes 6/2, which is the same as -3. And then we can just put those together, and we're going to get 3/2 as our answer. Now, you can also use your calculator and get there a little faster, but these are the algebraic steps that are happening. All right, over here, this could be a problem. We need to, because now it's a fractional or rational expression, so we need to check the bottom. And 2 times 3 minus 3 is not 0. So we're okay. We can just plug this thing in. So we're going to get 5 times 3 plus 2 over 2 times 3 minus 3. When I do that, I've got 15 plus 2, 17, and then 6 minus 3, which is 3, and that's our answer. Now, you will notice here I'm not writing limit. Once I substitute in the value, I no longer need to write the limit. If I'm just simplifying it, I still need to write the limit as x approaches whatever value. So that's why I'm no longer writing it here. All right, let's try these next two. So 2, that's not going to make this into anything that's 0. And this is going to be defined for anything where x is going to be greater than -2, so we're also okay. Why? Because I can't take the square root of a negative number, okay? All right, so I'm going to go ahead and just plug that in then. I'm going to get the square root of 2 plus 2 minus 1 over 2 plus 1. That's going to give me the square root of 4, which is 2, minus 1. We'll go ahead and write about 2 minus 1 over 3, which is really just 1/3. Awesome. All right, now these ones I know sometimes you guys have a little bit harder time. But there's no way for us to make sine undefined, so we're going to just go ahead and plug it in. So sine of 2, instead of theta, it's pi over 2. Now the 2's there are going to cancel out, and so really I've just got the sine of pi, and hopefully you remember your unit circle well enough to remember what that is, and it is just 0. Oh, that looks funny. We'll square it instead. There we go. All right, so let's take a look at some other examples here where that is not the case, where I can't just plug it in like I just did, okay? If I plug in -3 here, I'm going to get 9 minus 12 plus 3, which is 0, okay? Maybe I'll write that out for you to help you out. So -3 squared is 9, -3 times 4 is minus 12, and then plus 3, this is 0, okay? Same thing on the bottom here, I'm going to get -3 squared is 9, minus 2 times 3 is going to be minus 6, minus 3, that is also 0. So this is actually a problem. Later, we'll learn a rule that helps us deal with this, but we're not there yet. We don't know how to take the derivative, so we can't do anything with it other than what we've done in pre-calc. Let's take a look at these other two examples here as well. So if I put a 1 in the top here, I'm going to get 1 plus 4 plus 3, right? And if I do that, I'm not getting 0, right? I've got 1, 5, 8, okay? But on the bottom here, I've got 1 plus 2, which is 3 minus, that's 0. And that is a problem, okay? Over here, I'm going to plug in 1. I got 1, same thing, 8. And on the bottom here, I've got the same thing with 0, because all I did is change it from negative or positive, which when we're just subbing in doesn't make a difference. So for all of these, we ended up with problems, right? The first one, we got 0 over 0. The second two, we got a number divided by 0, which is still undefined. So we couldn't really do anything. Now, what we need to remember is that just because a function is undefined at a value of x doesn't mean that the conclusion cannot be reached about the limit, because the limit is talking about what it is approaching, not what it actually equals. So in this case, if I'm approaching -3 and I look at the graph here, right? If I'm approaching it from both sides, I'm approaching the same value here. It doesn't matter that the function doesn't exist. And so if I look, it tells me that it's 1/2, which you can kind of see here too, but just to make it clear, they put it in there for us. Now, when I'm approaching 1, I'm approaching this asymptote. And as I approach it from the left, I'm going down. I'm actually going to -infinity. And as I approach it from the right-hand side here, I'm going up to +infinity. So the limits still exist for all three of these, even though we couldn't algebraically just shove it in there. And so what we need to do then is take a look at these analytically, okay, and try to figure that out. So in pre-calc, how was it that we found discontinuities of a rational function in pre-calc? So that's twice. But how did we do it? We factored it, right? And we saw if anything could cancel and simplify the equation, because quite often it did, right? Especially if it's going to be an asymptote, it might, it won't simplify out. But if it is a point of discontinuity, then it canceled out. So let's take a look at that. And let's do that with that first one here. Okay, so we're going to tackle it like pre-calc. And so I'm factoring the top and bottom. If you need some help with factoring, guys, I got to be honest with you, you're going to have to go review that. Because in calculus, I'm not really going to be doing a lot of review on factoring, okay? But basically, I'm looking for something that multiplies to 3 and adds to 4, and so that's just going to be x plus 3 and x plus 1, okay? Then on the bottom, I'm looking for something that multiplies to negative 3 and adds to 2. Well, that's x plus 3 and x minus 1. All right. So then, of course, here that cancels out. That's that point of discontinuity. And so now I've just got the limit as x approaches negative 3. I haven't plugged it in yet. I got to write limit of x plus 1 over x minus 1. And now when I plug that in, now I don't need to write limit. I'm going to get negative 3 plus 1 over negative 3 minus 1, which is going to be negative 2 over negative 4, or just 1/2. The negatives cancel. All right. So based on our knowledge from pre-calculus, if a rational function has a non-removable discontinuity, graphically, that was an asymptote. That was the thing that doesn't go away, right? Since the y values do not approach one specific value from both sides at an asymptote, they can, but they don't in this case, right? Then the limit does not exist. However, we can determine if the one-sided limit exists still, and we're going to do that analytically here. So we know that this is an asymptote already because we saw the graph, right? So it doesn't cancel out, right? Like, and we saw it here when I algebraically did it as well. It's still on the bottom there. So instead, what we can look at here is the value of x, and we're going to get something a little bit to the left. We're just going to use something close like 0.9. Now, if I plug that into here, I don't actually care what the value is because I already know it's an asymptote. It goes to infinity or negative infinity. It's the only options, right? If I've got a line that's impassable and I'm approaching it, I either have to go up or I have to go down. There's no other options here. So what I'm doing is I'm just looking for the sign. So if I plug in 0.9 plus 1, it's positive. And if I go 0.9 minus 1, it's negative. When I look at these two things and divide them, that's going to give me a negative. So it's going to approach negative infinity. And we know it does because we saw the graph earlier. Same thing here from the right. I'm going to be like, well, what about something a little bigger than 1, like 1.1? If I put it in here, obviously a positive plus a positive is positive. And 1.1 minus 1, well, that's still positive. So this one is going to go to positive infinity. All right, let's apply this again here. All right, so write the equation of each piecewise function. So equation of the piecewise. So first of all here, if I'm looking at this first one, it's just a line. And that's going to be, it's negative. So negative, the slope is 1, negative 1. And then if I continue this down here, it's going to be minus 5. Okay, and my constraint here is that x needs to be less than negative 3. Okay, now I'm going to look at the other line because that's a little bit easier as well. So here my slope is again negative, but this time it's 1/2, right? Down 1 over 2, so negative x over 2. And if I extend that up here, it looks like it's going to cross right here at negative 1. Okay, and my constraint is going to be that x has to be bigger than 2. Now for this one in the middle here, this is a little bit harder. Hopefully you remember, but I can take that vertex form there, and basically it's going to be x plus 1, y plus 1, and not minus 1 when it's at negative 1. Because x is weird, all right? And then it's going to be squared, and then I got to move it down, so minus 6. This is our vertex form of a quadratic. And for this one, x needs to be between negative 3, not equal, okay? And it needs to be less than, but also equal, because it's filled in up here, than 2, all right? And that's going to be our restraints on it. Now, if we look at this, okay, let's figure out these limits. Can I approach from the right, or 2 from the right? As I approach 2 from the right-hand side, absolutely, I'm going to negative 2 there. Okay, now if I approach 2 proper, well, if I go from the left side, it's not 2, so the left side doesn't equal the right side. So this does not exist. Left side does not equal the right side. All right, next one is negative 3 from the left and the right. So from the left, I've got 2 from the right, negative 2 on both of those. So they did exist. And our last two here, as x approaches negative 7 here, that's just a value. It's on the graph, so it's going to be 2. Okay. And then on this one here, I've got it approaching negative 1. Hey, look, that's that vertex. And from both sides here, I can see that this thing is going to be negative 6. Now, technically it said let's use the equation, so let's use it real quick on that one there. So if I use that middle equation, x plus 1 squared minus 6, it's going to be negative 1 plus 1 squared minus 6. This is 0, and so I get minus 6. Same thing over here, negative x minus 5. well, that's going to be negative 7 minus 5 is going to give me 2, because that's positive 7. All right, guys, that'll be it. So, yeah, go ahead and do those practice, and I'll see you for the next one. I just realized I should probably show you the actual work up here for this one as well, since that one was a little bit different where you were not supposed to use the graph. So let's quickly look at it. So I'm approaching 2, okay, which means that I'm going to need to use both of these two equations in order to figure this out. So from the left side, it's going to be this, and when it's bigger, it's going to be this one here. So that means that I'm going to be using x plus 1 squared minus 6 is going to need to be equal question mark to negative x over 2 minus 1. Right now, we know it isn't already because it doesn't exist. But let's go ahead and prove this now. So 2 plus 1 squared minus 6, that's going to be 3 squared minus 6, which is 9 minus 6, or 3. Now on the other side here, where we're trying to figure out if these things are equal, we've got negative 2 over 2 minus 1. Negative 2 over 2 is minus 1. So minus 1 is going to give me negative 2, and 3 does not equal negative 2. Therefore, it does not exist. All right? Awesome, guys. See ya.